Welcome to Edwards Vacuum Laboratory Talk Podcast. I'm Dan Rutherford, and I've worked in multiple roles during my 24 years at Edwards, and I'm currently the Market Sector Manager for Analytical OEMs.
And I'm David Steele. I'm the Market Sector Manager for R&D, and I've been involved in vacuum technology for about 35 years, just over 25 years of that time at Edwards.
Hi, and I'm Todd Tevoet, and I've held various positions within Gamma Vacuum and Edwards Vacuum since 2009, primarily supporting UHV and XHV customers and sales channels in North America.
Today, we're going to be chatting about metrology and specifically about basic, commonly used vacuum gauges and why they're important. Today, we'll mostly be discussing direct reading gauges like dial gauges and capacitance manometers. So let's start by talking a little bit about why we use vacuum gauging.
Well, I've seen loads of installations that don't have any gauges at all.
Well, some applications are just fine without any instruments. If it works, then it works. But I've always thought that that's the equivalent of shutting your eyes and hoping for the best.
Right. Probably most of the time everything's going to be just fine, but when it's not, then you're just kind of left with guesswork as far as what could be going wrong with your system.
So having a good gauging, good vacuum gauging to monitor your vacuum system is invaluable for either fingerprinting initially or mapping out how your system should be behaving. And they're really useful diagnostic tools when troubleshooting, if something goes wrong.
So selecting your gauge for measuring vacuum can seem pretty confusing and even overwhelming at times. How does a person know what is the best gauge or gauges to use for their system?
Well, there's a couple of major decisions that you have to make when you're going to pick out a gauge for a system. The first is the pressure range over which you're going to be measuring. So, for example, are you only going to be going to the rough or medium vacuum level with an oil-sealed rotary vane pump or a scroll pump? Or are you going to be going into the high vacuum range, something like a turbo pump or a cryo pump? Maybe you're even venturing into ultra high vacuum XHV ranges with an ion pump or other capture pump. Different types of gauge technologies are required to cover a large pressure range, or maybe just to concentrate on one specific pressure range.
And once you pick the type of gauge you plan on using, the next decision is a bit like dealing in real estate, isn't it? I mean, the three very most important rules are location, location, location. And really, this boils down to placing your gauge as closely as possible to the position that you actually want to measure the pressure at.
Right. So if you have a long pipe, for example, in between your vacuum chamber and the pump, and you want to measure pressure at the chamber itself, you really want to mount the gauge nearest to the chamber or in the chamber and not near the pump end of it.
Yes, and whilst that might sound obvious, it is surprising how often that does get overlooked. So, for example, if you want to monitor the pump inlet pressure itself, put a gauge right at the pump. And if you want to measure at the chamber, put a gauge on the chamber or as closely as possible.
I know that sounds a bit silly at first, but quite often, the gauge location does have to be a compromise, particularly if you're adding gauges after your system is already built. We got to keep the pipe work as short as possible too, right?
Yes, that's right. Much like connecting pumps to systems, compromising the pipe work on gauging can have a major impact, mostly on the time that the gauge takes to react to changes in the system.
So similar as pumping, keep the pipe work as short as possible and trying to maintain the same size pipe work as the gauge fitting to get a really good starting point.
Yep.
There's some other practical tips like positioning gauges so debris can't accidentally fall into them and taking precautions to protect them from extremes of temperature, for example.
Yeah, like in a furnace, you want to mount the gauge on an elbow so it's not a direct line of sight with the hot zone.
Yes, that's right. A simple elbow fitting is a good example of a very effective low-cost optical baffle.
And that works for coating applications as well. By breaking the line of sight between the gauge and your system, you'll reduce the coating or any other damage on the gauge and interference with your gauge.
The other things to consider are the gases that the gauge is going to be exposed to. So, for example, if you're only pumping air or nitrogen, residual gases, then no real particular precautions need to be taken with the gauges that you pick. But if you're pumping something corrosive, dirty, flammable, otherwise nasty, or something with other special properties, then those characteristics need to be taken into account for both safe and reliable operation of your instrumentation.
And at the end of the day, if you're still just really not sure, Checking with the gauge manufacturer like Edwards is a really good idea.
I've heard those guys know their stuff.
Just about the first sort of vacuum pressure gauge was a simple U-tube just filled with water, and I am going back in time here a few hundred years. These usually get referred to as manometers, although technically a manometer is simply any device that's used to measure pressure of a media like gas or a liquid. U-tube manometers are really easy to construct by just making a long U shape using a clear piece of pipe with one end open to atmospheric pressure and the other end connected to the vacuum system. When there's a differential pressure, when you pump against the vacuum system between the open end and the vacuum system, atmospheric pressure on the open end pushes against the surface of the liquid. And as the pressure in the vacuum system drops, the height difference represents the vacuum level. And commonly, water scales are used in inches of water.
So now we're going back to an earlier podcast. That's where the unit of measurements come from.
Yes, and that's why vacuum readings in inches of water are usually expressed as a negative gauge pressure reading because it's relative from atmospheric pressure.
Well, but the problem there is, doesn't water start to evaporate, to boil under vacuum, even at room temperature?
Yes, at room temperature, it'll boil at around 20 millibar, about 2% of normal atmospheric pressure. So this sort of water-based gauge is only really useful for rough vacuum measurements, and you won't find them much these days outside of things like vacuum extracted cabinets or vacuum chucking. Uh, and they're also used in things like measuring differential pressures, the effectiveness of sealing drafts in buildings.
So what about mercury and for manometers?
Well, if you use a different fluid like liquid metal, mercury, that's got a much, much lower boiling point or vapor pressure than water. It's a 10 to the minus 5 millibar at room temperature. So you can use those to measure much lower pressures.
And specialty versions of manometers, like the McLeod gauge, for example, were used for a very long time as a vacuum reference standard, and it can be used to get really accurate pressure reading down to the 10 to the minus 3 millibar or millitorr region. Though they're they're very fiddly to use, though.
Yeah, they are. They're not plug and play vacuum gauges by any stretch of the imagination. It's all manual stuff there.
Unless, need to say, mercury is pretty nasty stuff to have around, so you don't see that kind of gauge anymore.
Yeah, that's right, Dan. Mercury is pretty toxic stuff, and outside of very special applications, these usually require permits to use mercury in most parts of the world, and mercury manometers aren't used that much these days.
Well, listen, I know you really want to start talking about practical vacuum gauges, David. So let's start off with clean duty type applications. In other words, where you're pumping clean, dry, non hazardous materials like just standard air or even just nitrogen.
Right. So for rough duty vacuum down to just about 10 torr or 10 millibar, or about 1% of atmospheric pressure, there's lots of choices, mostly inexpensive for measuring low pressure in this range.
Yes, that's right. You've called it exactly right, Dan. Probably the most widely used type of gauge is a simple dial gauge, and they just look like pressure gauges, just round dial gauges. For example, the kind of thing you'd see on a gas bottle, but they're calibrated for pressures lower than atmospheric pressure. You'll often see them as combination gauges where the pressure can be positive above atmospheric pressure or negative, a vacuum. So it's quite common to see these with vacuum range units as negative vacuum, which we talked about earlier. That's a gauge pressure reading rather than an absolute vacuum pressure reading.
Right. And these can give a coarse pressure reading, but if that's all you need, these can make a really good, really quite good gauge for you. But if you need a little bit more resolution at lower pressure ranges, then a vacuum specific gauge is probably a better idea. A vacuum specific gauge will also be atmospherically compensated for, which means that regardless of any changes in the external atmospheric pressure, the gauge will always read the same. It will be reading absolute pressure rather than gauge pressure relative to the current surrounding atmospheric pressure.
And you can get these with a variety of full scale range indications. For example, Edwards sells them with 1,000 millibar full scale or 100 millibar full scale and so on. So you can pick whichever full range scale is most useful for your application, or even use a couple of them at the same time.
Well, another big plus about this type of gauge is you don't need any external power at all, not even a battery, to make these things operate.
Right, right. So when you look inside them, they look very similar to old school barometers with a sealed pressure capsule that moves in and out as the pressure surrounding it changes. This movement is then amplified by some gears and finally a needle that indicates a pressure on a circular type scale. A bit like a clock face, right? One of the drawbacks, of course, is your gauge scale is of one set units and you can't really convert the gauge into another set of units.
Well, Sharpie could do that, right? That would work.
Frequently, yes, that's a pretty good solution. Put a mark on the gauge dial indicating the pressure should be lower than this mark, for example.
It's worth noting that was these types of atmospherically compensated gauges, they don't tend to be very tolerant to dirty environments because the entire mechanism is under vacuum and it's exposed to the process.
So let's now say you have a dirty process that would deposit dirt or debris into the gauge. What would you use then?
Well, diaphragm type gauges like strain gauges, sometimes called piezo gauges or capacitance manometers, they make really excellent solutions for dirty processes or other difficult applications.
Right. This type of gauge has a sealed capsule with a vacuum reference on one side and the vacuum environment that you want to measure on the other. The only thing exposed to the vacuum environment is a sheet of thin metal, but no hot filaments or high voltages.
I've seen there's a lot of different names used for capacitance manometers, and it seems to confuse everyone too. There's capacitance manometer, capacitance diaphragm gauges, and some are trade names like Edwards. We have a trade name Baricel, but they're all still based on the similar measuring principle.
That's right. So for simplicity, we'll try to stick with the generic term capacitance manometer or CapMan. They're the gauge of choice for both high precision applications and ones that have difficult or corrosive gases in them.
So, how do they measure pressure, vacuum pressure?
Well, you've probably seen videos of someone putting something that's elastic, like a balloon or even a marshmallow, in a vacuum chamber and pumping it down to a low pressure.
Yeah, they expand, they get bigger.
Right. So diaphragm gauges actually, most direct pressure reading gauges operate on a similar kind of principle using in a Catman's example, using the elasticity of a thin diaphragm as the physical force against the pressure to be measured. As the pressure drops, the diaphragm tends to move outwards into the vacuum environment, and as the pressure being measured increases, the vacuum pressure gets higher, it moves inwards. The movement or the deflection of that little diaphragm is then used as an indication of the pressure.
Right. So, because the only thing being exposed to the process environment or the vacuum chamber side itself is a metal diaphragm, these types of Capmans, like the Edwards 7000 series gauge, tend to be a really good, really rugged, and tolerant of difficult process conditions.
Yeah, that's right. They get used, I mentioned earlier, a lot in the semiconductor industry, for example, where really aggressive chemistries are used, nasty gases, lots of corrosive materials. You can even heat them up to prevent material condensing inside them and to help compensate for high temperature processes that might affect the pressure reading otherwise.
And as well as being very tolerant to dirty environments, capacitance manometers are incredibly sensitive as well, aren't they?
Yes, they've got one of the best accuracy levels of commonly used vacuum gauges.
Yeah, but these gauges usually have a fairly limited range of just 2 or 3 decades of pressure, don't they?
Yes, I mean, compared to some other types of gauges that we'll talk about later, that's quite a small pressure range. So you do have to select the full pressure range that's important to you, or you may have to use multiple gauges to cover a wider range if you want to optimize accuracy or resolution over a wide range. This limitation is simply a result of the mechanics of moving a thin metal diaphragm to indicate pressure. That does have to be considered when you select a Catman.
So typically, you'd pick a capacitance manometer with a full scale range matched to your application, say the pressure range that a coating process will be carried out over. You'll get the best accuracy over the first 2 decades of pressure and reduced, but still very usable accuracy to the third decade.
Okay, so I got it. So, what about something like the Edwards active strain gauge that we use, the ASG2?
Well, these share a lot of similarity with the capacitance manometer as they have a thin metal diaphragm with a vacuum reference on one side, but they typically have some sort of piezoelectric device as the sensor bonded to the back of the diaphragm. The movement or stretching of the diaphragm changes the electrical characteristics of the sensor. Some external electronics will then convert that change into a pressure reading. Commonly, it's a simple voltage change, but the gauge output could be 0 to 20 milliamps or even direct to digital data. Sometimes it can just be a voltage output, and sometimes it can be used to drive a display directly. It all depends what you want to do with the reading.
So all these types of gauges, the Capmans, the strain gauges, and even the dial gauges are what we refer to as a direct reading gauge then, right?
Yes, that's right. They use a direct physical force characteristic, the physical pressure of the vacuum environment compared to some other reference. Indirect reading gauges like Pirani gauges, which we will talk about in our next podcast, use some other characteristic that's indirectly related to pressure within the vacuum environment, such as thermal conductivity with a Pirani gauge or the ability to pass an electric current with an ion gauge. So most indirect gauges, in fact, most modern vacuum gauges, are electronic instruments which have some sort of electrical output that represents the pressure reading.
Okay, I got it. All right, well, let's wrap up that today's podcast with that little last bit of information.
In our next podcast, we're going to tackle part 2 of vacuum gauges, which is indirect pressure reading gauges like Pirani and ion gauges.
Nice. So please continue to check back with us in the future, as we're still hoping to release a new podcast about every couple of weeks. And if you'd like to reach out to us with any questions that you would like us to answer during one of these future podcasts, please send an email to podcast@edwardsvacuum.com, all one word. We'd love to hear from you, and we'll do our best to include your questions in future podcasts.
And if you have an immediate need for information, you can always reach out to one of our technical support folks here at Edwards Vacuum by emailing info@edwardsvacuum.com.